Let's start with our introduction as to why we do machine learning. And you've seen a lot of the reasons for doing machine learning in the previous class. These are my reasons. And I'm going to start by an introduction to machine learning with an introduction to how we do things, how humans do perception. So a lot of you have seen this, and if you have seen this, please don't spoil it for the rest. So I'm showing you here two images, and I'm switching between these two images, and there's a difference between these two images. So the first question is, who has seen this video before? I think a great many of you. Okay, for the other half of the class, can you tell the difference between the two images? So who sees the difference? That you hadn't seen it before. Who doesn't see the difference? And this is not an IQ test. Let me tell you that the difference is something that's very important. It's a lot of pixels, and it also is an object that is essential for aeroplanes to fly. And it usually goes on the wings. And if you haven't yet seen it, it's the wing. I should update these videos. There's many more similar videos. This phenomenon is called change blindness. It's a term that was coined by Brent Rensick a couple, I think, decades now. And if you think, okay, that was just a trick, and once I can tell what's missing, I will always see it. Like if I play this video again, I'm not going to fool you. Now I'm going to play a video that some of you have already seen. And you will still not be able to see most of the content in this video. And so here is a video that I got from MIT. I'm going to ask you to follow the instructions at the top. Okay, so let's start with those of you who haven't seen this video before. What changed?
The building, something with windows.
The building.
This time on the right, with those with two stars, it wasn't there previously.
Okay, the sign.
The hotel.
There was a bar sign in the middle building.
There was a bar sign. I never noticed that. I learn every year.
Yeah, the color of the door.
The color of the door changed. Who saw the color of the door changing? Who didn't see the color of the door changing? Okay, it did change. And in fact, this whole building that is now sort of pinkish, salmon, that was a different building before. It was a brick building. This door was different. You could have been suspicious that this sort of fence is broken here. Okay, so this doesn't seem very safe. Put a door up there and then cut the wrought iron so that someone could jump off the door. So even if sort of common sense would have told you something's wrong with the scene. So before there were windows up here, and this wasn't broken. There was a sign. There were people here. More people have appeared. Some people have disappeared. The scene has changed dramatically in front of your eyes. And none of you was able to see all the changes. This is the original image. So as you can see, there were people here. There were less people here. The door changed. There were windows. There was a sign. It was a complete brick building. So most of this image actually changed and you were not able to perceive those changes. A lot of people don't believe this when they see this. So I'm just going to play this one more time. And this time you'll probably, if you focus attention in one particular area of the image, you might be able to see some of these things changing. The price to pay for focusing attention and seeing that one thing changing is you will not see the rest changing. And this seems crazy, right? Because you're looking at this image. How many of you believe that what you see in the world is there? Okay, this is like you believe you're seeing it, but you're not seeing it. Okay, you're saccading this image, and you're at high resolution is something of the size of your thumbnail, and you're going about 3 times a second, and that's what's going into your brain. There's 3 images. Vision is a temporal process. You have limited memory in your visual buffer, so you can't store too much. You can't store this whole information. And so on. Vision is an extremely complex process that we don't understand. When we've made incredible progress, as I'll soon show you, but we still don't fully understand it. And learning is a big part of vision, as I will argue also in the rest of this introductory lecture. But if we cannot introspect into the world of how we learn to see things, then there is no hope that we could ever program a vision system. It's just we're completely unable to introspect. One of the biggest problems with artificial intelligence is everyone thinks they're an expert on it. No matter who you are an expert on artificial intelligence because you know how you think, you know how you see, you know how you hear things, you know how you make decisions. Turns out that all of those things are false. We get fooled by our own minds all the time, and it's part of survival. That puts us in a quandary because we want to build intelligent systems, but it's very hard to build intelligent systems when we don't have good introspection. So that's one reason for why we need something different other than just introspection to go about solving this. Here's another reason. Suppose you want to recognize giraffe. Do any of you have any trouble recognizing that creature climbing the tree is a giraffe? As ridiculous as that looks. I don't think anyone has any issue with recognizing that, or that the big blobby one is also a giraffe, the one with the twisted, things that are completely impossible in the world are still giraffe. Try to build machines that are capable of understanding all these invariances in the world and try to code this, and you would sort of give up on coding. So coding is not the way to go. The machine learning way to go is if you want to, for example, understand what a face is, and you want to be able to look at an image and say that's a face, just like you would say that's a giraffe, you want to now say that that's a face. It's not to try to code what a face is. And people have attempted this. I remember about a decade or so, 15 years ago, I was doing some consulting in Japan, and there was a system that was working really well. You could sit in the driver's seat and it would quickly detect your face, and so the idea is you would know exactly where you're looking and be able to tell whether you were driving attentively or not. And it was working really well for them until a friend of mine of Scottish descent sat and it completely failed. And we were trying to understand why doesn't the system work, until we realized it's being tested in Japan. Everyone has dark eyebrows. What this thing has learned to do is detect dark eyebrows on images. And it worked with me, but it didn't work with my friend. And this is the problem when you try to code these systems. So there's always this sort of rare events that throw you off. The machine learning way is collect a lot of images of faces, label them as faces, collect a bunch of images that are non-faces. That may or may not be necessary, as we'll see later. And voila. That's how these devices exist. We all take them for granted. Everyone has a face detector and an image. It's kind of funny that in computer vision, folks decided to put this box around it. This first came up in the 2000s with a paper on boosting, which some of you saw last term. And now I see that even the TV ads have this box around. People just expect this to be a normal thing that a machine should do. Another thing about intelligence, once you figure it out, it's no longer intelligent. It's obvious. And you can do this with any object. Like, for example, pedestrians. And if you do pedestrians, you can sort of do this sort of thing, automatic driving cars. Automatic driving cars will be soon part of our reality, I hope. We managed to deal with all the legal issues and economic issues to make that a reality. Currently in the world, 1.2 million people die every year in car accidents. And don't you think that because you don't drive, you're okay? Turns out most of those people are pedestrians. It's barbaric that over 1 million people are dying every year, and we don't do anything about it. And we could just fix it by make every car be automatic, self-driving car. So when people are talking about the dangers of AI and so on, the dangers of building AI, number one, by not having self-driving cars, we are killing 1 million people every year. We shouldn't let that happen. And so I think that by itself is good enough reason to take this course and to make good vision systems, good AI systems available to the world. And of course, they're also great for entertainment. You can use the same technology to track hockey players. Me being Canadian, I have to champion hockey. And once you know where the hockey players are, you can sort of design strategies. You know exactly where each player was at each part of the game. So you can improve entertainment systems and so on. You can automatically generate games of teams that play like the real Vancouver Canucks, or in soccer parlance, football parlance, that play like the real Man United. Recently there have been some advances on doing data processing with neural networks, which were models that were very popular. They have been popular sort of in the 80s and then went out of favor, and that have recently come back and become very popular. And not only popular, but actually successful. Successful to the point that companies are investing millions, if not billions of dollars right now on these technologies. And a lot of them were inspired by neuroscience. And it's really, the inspiration comes from neuroscience, but it also comes from statistics, from optimization, mathematics, great advances in computer science. And none of this would have been possible if we hadn't invented, without all the inventions in hardware that we've made over the last few decades. GPUs, central to all this. Being able to do distributed computing in the new hardware platforms is essential. Being able to storage, being able to store videos, we take it for granted. When I was doing my PhD, which I ended up in 2000, you only had 6 images that you could play with in your computer. It seems like a joke that this wasn't that long ago. The way we interact with computers and data has really changed dramatically. We're very lucky to have lived through this in this stage in the world. In terms of neuroscience, there's been some interesting findings. We have neuroscientists here, so I'm not going to embarrass myself too much by spending time in this. But the basic idea here is that the brain's a machine, it's a biological machine. I'm not going to go into the metaphysical aspect of it. I'm going to take a very practical view of it. That if anything, if I have recollection of anything that happens in the world, it's because some cell is firing or stopped firing. And so in particular, there are cells that will fire depending on where your position in the world. As shown by this diagram here, there's place cells that will fire depending on where a rat is. And if you actually take, I guess you do these experiments with your rats. If you put, not you, but folks put wires on rats, and they're able to measure it, you'll see that there's some cells that will fire depending on where you are in the world. This is how you know where you are. And in fact, you also build maps of the world, and these maps reside in your brain, and they're all based on the firing pattern of your neurons. And very recently this year, the scientists received a Nobel Prize for some of this work. Actually looking at these sort of cells, at these grid cells in the entorhinal cortex that allow you to actually get a map of the world. more interesting, what really drove a lot of the models that exist today and that I will describe was an experiment by chance by Hubel and Wiesel several decades ago, where they had a cat looking at, and you can YouTube this Hubel and Wiesel cat, and you'll see the actual cat and the light. So some of those videos are not for people who love cats. But you'll see a beam of light here, and then what they realized that when the light is in a particular orientation or moving in a particular orientation, there's these cells. The experiment is far more complex, and there's simple cells and complex cells and so on. But let's suffice it to say that when the bar is moving in a particular orientation, as shown in this diagram, the neuron fires. Otherwise, the neuron doesn't fire. And these are neurons that I'm measuring are here at the back of your head. The first neurons in the visual cortex, V1. And so basically what this is saying is that the neurons at that stage, they're coding all the different angles of things in the world. They're coding for edges, changes in intensity, and so on. And if you take a little bit of cortex, that's pretty much how they would be placed, and they would be coding for different angles. And we know this is learned because you can take a cat and make it live in a world where there's only vertical lines, and then this cat will not develop receptors to horizontal lines. Or I think, how do you keep this cat standing all the time? I found this picture, and I'm not quite sure how they do that. But one that is much more plausible is you cover one eye of the cat, because the optic nerve crosses and projects to different parts of V1. In one side of the cortex, that eye will develop detectors, in the other part of the cortex not. And I think folks have done those experiments. So the important lesson here, the important outcome here is a lot of vision is learned. So the learning mechanism is quick. And so that's the idea. So the idea is you sense a small part of your image, you saccade to a part of your image. This is basically one of the saccades. I mean, it's not round, it's not square, it's round, but I've just drawn it here as square. And then the idea is that you have many neurons. In this case, we have 4 neurons. Each of these neurons is basically from each pixel in this image, there is a line that goes to each of the neurons. And so if you look at each line, and since there is one line from each pixel, the lines themselves form a grid. So if you were to cut at the lines and you look at the value of these lines, the sort of the amount of, shall we say, conductance that's allowed through these lines, you would get an image that looks like this. And what that means is each of these 4 cells corresponds to one of these 4 images. The cell, let's say this cell here, the leftmost red cell, is the top one. So that means that that cell will fire every time the image that it looks at has a difference between white and black. In other words, an edge. So if you look at an edge usually has one type of color, and then think of it as black and white. You would have something that changes in intensity. So white being a very intense part of light, black, low part of light. The second neuron is detecting something that's more sort of cornerish. The third one is detecting 2 vertical bars. The other one is looking at a color filter. We call these filters as well. So these neurons at the lowest level are just detecting little changes in the world, little brush strokes, if you will. But you know the power of brush strokes. With brush strokes, you can compose many paintings. Just go to the National Gallery, convince yourself. People have trained, and one of the things we will learn about in this course is how to train convolutional neural networks. And the idea of a convolutional neural network It's something that's not necessarily biologically possible, but it's very much inspired in terms of its training, but the architecture is very much inspired by Hubble and Wiesel. The idea being that you have these filters, these small images that will detect edges in a particular part of the image, like it might detect this inclined edge here between the house and the sky. And then that's the first layer of neurons. Then it goes to a second layer of neurons, sort of complex cells. And the first layer, they tend to be, make sure that they're sort of like AND operations, and the next layer, they're like OR operations. And this is sort of what we find also in our study, in the studies of Hubble and Wiesel, of simplest complex cells. OR is sort of invariant, so things could move a little bit and you would still be able to see the same thing, because vision has to be invariant. If the light changes a little bit, I still have to recognize you being the same people that were here 5 seconds ago. At the same time, I need to be selective. I still have to recognize that it's the same person that's there. And these architectures have several layers. People nowadays build them with 20 layers or so. Those are the latest in terms of object recognition performance. These models are state-of-the-art for object recognition. So there's these competitions for object recognition, and about 2 years ago, Alex Krzyzewski and his teammates from the University of Toronto, they entered a computer vision conference, and they completely trashed everything that the computer vision field had ever developed until that point. Their performance was so much better, and their system was completely trained. And the only sort of prior knowledge that they built into it is essentially the prior knowledge that goes into building this architecture. It's called a convolutional neural network. Jan LeCun has championed this for a long time. Jan LeCun heads AI now at Facebook. A lot of this work is also based on something called the neocognitron, which was Jans told me that he's actually looked at neocognitron at some the papers throughout his life. Having talked to Fukushima, who's the creator of the neocognitron, he told me that when he was working in Japan, he was very much inspired by the experiments of Hubble and Wiesel. So there's definitely, the dream has come from neuroscience, and then it allowed people to realize it was feasible, and it led people to design these architectures. Now, in the previous image, I showed you the filters for when you look at images. If you go deeper in these models, so in the first layer, when you take, essentially what you do is you take a bunch of images and you take labels for image. So just like we did for faces, there's a face, you will take images like this is a cat, this is a camel, this is a bike, this is a house, and that's essentially the data that this competition provides you with. And when people train these models, in the first layer, they learn the filters that are shown here. So vertical bars, so this is very similar to what we had before, but in the second layer, you start looking at things that look like more interesting compositions, like edges, vertical things. And what these guys, Matthew Zeller and Rob Fergus is at Facebook, Matthew Zeller has his own company, he won the big competition last year. This year the competition was won by Oxford, by Karen Simonian and Andrew Sisserman, who are here in information engineering. Karen is now working at Google DeepMind with me. And so they looked at what are the images that are most similar to the images to these filters, which are what each cell responds to. So a neuron will fire when it sees these different circles. So each of these images correspond to one of the neurons that were automatically learned. And so these are the type of image patches that would match those neurons. If you go higher up, you start seeing neurons that fire for particular textures, like you start getting these type of patterns. And eventually you start getting dog neurons. So neurons that fire for particular types of dogs. and neurons that fire for birds, parts of birds, as you can see here, bird legs, dogs, and so on. This, again, in neuroscience, they're called grandmother cells, and IT. And so it's been well known. I mean, there's this, they call it the Jennifer Aniston cell. That if you show pictures of Jennifer Aniston, there's the cell will fire. All those experiments were supervised, and supervised in the sense that the way the data was presented. I will make this more, I'll define this more clearly as the course progresses when we go into the details. But the idea is you had a teacher telling you what the output should be. If the image was a zebra, then the output should be the word zebra. So you should be able to produce zebra. Of course, throughout life, we don't get supervision at that level, and we still manage to learn all this automatically. So a lot of the learning happens in an unsupervised manner, or by trial and error, something that we model with reinforcement learning, which I will cover at the end of the course. And in unsupervised learning, there is no teaching. So Google a few years ago did this experiment where they took some models by Apo Kivarinen of the University of Finland, and they just made many models with many layers of that sort of basic model, and they added the same operations of the pooling, convolutions and pooling that were common in the ConvNets. And they were able to, just by making this network watch YouTube, so it takes YouTube in and it tries to generate YouTube. So that's the basic idea of reconstruction. That's a great principle for learning, and that's the most important thing about learning. If I close my eyes and I try to simulate what I think I'm going to see in front of me when I open my eyes, and if I'm imagining an African savanna full of lions, then I have to learn. Right, because what I'm seeing and what's coming from my mind don't agree, and so I need to adapt. So simulation is very important to learning, and in fact, a lot of learning we'll see as just different ways of doing this. If you can hallucinate well, you can learn, and so what they do is by doing this, and this is, by the way, also very much tied with things like schizophrenia and so on. This learning these mechanisms, coming up with computational theories of these models, will hopefully guide neuroscientists to probe the brain and hopefully design better drugs eventually to help people with mental disorders. So what Google did is they actually were able to learn neurons that were actually detecting faces and counts, because that's what you find in YouTube. And this was in the New York Times front page, and so this was very popular at the time when it came out. We're going to go over this model in this course. It's actually an easy model. All the things that people use now, so all the image search that you use, and whether you use Bing or whether you use Google or the thing that says that labels your face in Facebook, the device that is able to tell what clothes you're wearing when you take a picture and put it anywhere online, that's all a ConvNet. Okay, so every company now is using this technology to basically know what's in a picture. So it's very much part of all these companies, all these technologies, improved image search, video search. It hasn't quite hit video. There's still big issues of scaling, but eventually it will get there. And also speech recognition, because when you learn, there's no distinction. We don't separate images from video or DNA or audio. It's all data. It's all the same. It's signal. As long as we can extract the features from signals, we're able to apply these techniques. And why does it work? At a very high level, think about it. The optical nerve probably has about 1 million fibers. So let's say that you get an image that's 1,000 by 1,000 pixel image going into your head. Sort of very rough calculation. It could be off by an order of magnitude or so, but it doesn't matter. Now, if that image was black and white, you have 2 to the 1 million possible images that could go into your head. But that's more than what scientists speculate is the number of atoms in the universe. So if you wanted to do computation and represent all possible images in the world, our brains would not fit in the universe when you do these very rough calculations. And so that must point out that there's something else. And my speculation here is that the world is actually very commonplace in the sense that there's a lot of structure in the world. There's a lot of continuity. You don't expect, if I'm seeing a bit of white, I expect that white to prolong. Same with sound. If I'm hearing sound at a certain pitch, I expect that in the next microsecond it will still be at that pitch. Things don't change abruptly. I'm not seeing salt and pepper images in the world, but I see very regular images. And then what we're extracting, in fact, with these models, is the statistics of the images, the statistics of the sounds, the statistics of the data. What are the common compositional patterns in the world that if we knew those compositional patterns, we could synthesize any video or we could synthesize any sound. We could synthesize the universe. Here's another application that is very common, language. Language is also very regular. Most of the time the conversation you hear at the coffee shop is sort of deja vu because you've heard it before, because people just say the same things all the time. They use the same expressions. Occasionally there's that beautiful difference, and of course there's a lot more to intelligence. But there's a lot of regularity, so you can also exploit, there's certainly patterns in language to exploit, sort of verbs coming after nouns in English and so on. So these models are also analyzing text. They're able to, for example, predict whether a sentence is being positive or negative. So if you launch a product in the market, you want to know how much people like that product, and now there's automatic ways of doing that. So this is big because there's a lot of products whose value you can only ascertain once you have consumed. Things like movies, you can only know the value of how much you're going to like a movie after you watch it, or the same with I know lots of things. Like in this case, I found this cool one. It's from TripAdvisor. It's Sidekick. So you only know how good a psychic is once you try to psychic. This one's not very good, it seems. Right now, the push for these models and some of the companies, just to give you an idea, is, and I think there's a push at all companies, even though I put Facebook here, but there's something that Apple Siri would be very interested. You exist in a social network. Imagine you're in Facebook, you see an image, you click on that image, and you talk to your computer, and you say, who might want to watch this with Siri? Who do you think is going to want to watch this movie with me on Friday? And you would like the Siri or the Google Now or Facebook to tell you your best bet is Phil because he likes Downey Jr. So there's a lot of push now for making these machines of multimodal, combining different types of data, just like animals combine different modalities. A lot of the recent push has been for models that also have state in them, that have memory. And so up to now we've talked about this sort of one shot in time, where you see an image, you say what's in the image. But some things involve memory. Memory is essential. We can't just erase our memories and expect to continue tomorrow. And so right now we're building networks that have memory over time. That's going to be part of the course as well. We're going to go over them. And one of those nice things you can do is you give it a sequence as input, and the models learn to predict the temporal sequence. And in between these boxes, there will be networks that have memory. And so we're going to learn how to implement these memories and how to maintain things over time. And what people use these for these days, like Ilya Sutskever, is he takes something in one language, English, he outputs something in a different language, Japanese. In other words, it translates. So you basically, if you take sentences in one language, sentences in another language, you train one of these models and it learns to translate. And so there's a big push. These models have actually been quite successful. So there's a big push for doing translation with these models. Likewise, if you take a sequence in one language, you produce a sequence of words, you produce a parse of that sequence. So you learn to automatically parse. So for people who believe we're born with parse structures in our head, that might be this universal grammar argument, these models are seriously questioning whether that's true, because they're showing that you can learn it. You can learn grammar. The other thing that they can do is, I mean, you can imagine all the things you could do. This could be a sequence of code, and here comes out an execution of the code. And as crazy as that might sound, these machines are actually able to do that right now. So you'll find on the web, if you look at things like some of the work of Ilya, is doing exactly that. It's doing interpretation. One of the projects, DeepMind, that one of the guys that, by the way, has done a lot of work, we'll get to see a lot more of his work, Alex Graves. He presented these slides recently at a conference where he was showing how some of his, unfortunately I don't have the video, but I'll try to play it for you if I get my hands on it. But some of his colleagues at Google DeepMind were basically generating a full video. And someone else from Montreal actually presented a video at NIPS doing this sort of, a different model at NIPS, machine learning conference in December, showing the same sort of thing, how it's, for some simple things like these Atari games, you can actually generate a video of what's going to happen in the future. Because imagine if you can generate a video, then it's like our brains. We have this huge black spot in front of our eyes because there's a blind spot because of the optic nerve. And as I saw you with the illusions at the beginning, you're only seeing a few things, and yet it feels like we're seeing this all. Because we have good generative models in our brain that are able to fill it in and make us feel like we're seeing this whole scene. And so we're trying to build machines that are capable of doing that, because that is very useful for decision making. If you can imagine what you're going to find somewhere else, then you can decide whether you want to go there or not. Alex had a slide with this that I stole from him, and one of these, I believe, was written by a human, and the other ones were written by his machine, by his neural network with time and memory in it. Can you tell which is human? I actually don't know which one was the human, but the point being that they're so alike, so plausible that that they sort of start telling you that for some of these tasks, machines are performing incredibly well. Phil Blossom here in Oxford has also been doing a lot of good work on this, for doing translation, for doing dialogue understanding. You talk to a machine, the machine needs to understand whether you're complaining or asking to increase the order or something like that. Another type of learning that's going to be very useful is learning that involves decisions, action. Not so far we've been talking about perception, so you see the world. Perhaps with the recurrentness, where you have sequence here, sequence output, you could already see that the sequence here could be speech, and the output sequence could be actions. So you could build a game where you have a sidekick, and you could basically You could be playing a game, and then you could be telling your sidekick, go around those guys while I shoot these people, and so on, in one of these shooter games. And you could instruct an agent by voice to perform sequences of actions. And you could train it, provided you can get the data. We're going to see something called reinforcement learning that comes up with models of acting optimally in the world. And there's been sort of great progress in that area by marrying essentially all the deep nets, these neural networks with reinforcement learning. We're also going to look at a bit at the imitation learning, which is a big part of learning. It's how we learn to imitate other creatures. And as you can see, monkeys imitate. A lot of cute creatures do. And these are agents. Actually, can you tell which one is human, which one is machine? And here the chicken has to cross the road on an American freeway, as you can tell by the direction of the traffic. And actually, the game is called Freeway. If it hits the car, it gets sent back, but it doesn't get penalized. It only gets points when it gets to the end. And this is interesting, because here the signal, the supervision is very delayed. The supervision only happens way in the future. You could be random walking, and you're getting no supervision. It's only when you get to the other side of the road you get a point. And a lot of times, when you're, for example, playing chess, and you win, and then you wonder, what made me win? What were the sort of secret, what were the important parts? So that's a problem called creator assignment or reinforcement learning. We're going to look at it. Do any of you care to... which one is machine? The one on the right is a machine? Why? Because it's being more efficient? It's getting more points, even though it started at the end. Actually, I showed these videos for the first time at the CMU Machine Learning Summer School, and that was at the point in time where, parallel to my lecture, there was the game of Germany-Brazil. So I don't know if you remember that one. So the joke was that on the right was Germany, on the left was Brazil. And far more efficient at scoring lots, and actually Brazil was even worse than this one. Actually, it turns that they're both machines. They're just two machines that learn too, so I kind of tricked you there. So basically, a lot of machine learning is about extracting good features from the world. I'm going to go for over now 5 minutes, and then we'll take a 10-minute break. Extracting good features from the world to solve predictive tasks, decision tasks as well. They're not just useful for AI, as I've sort of championed in this course, as I'll go in this course, but they're very useful for practical applications, like finance, doing anywhere where you need to do any forecasts, and you want to do forecasts, and you want to be able to also have good confidence bounds on your forecasts. Missing data. So a lot of times you know that which movie someone likes, but you don't know if they will like some other movie, and you would like to compute the probability that they will like that movie. So you want to fill in something that's also called imputation, filling in the missing information. Detecting anomalies, that's a very important part. So for security, being able to detect something that you learn a model of what's normal, and then whenever you detect something that's slightly different, you want to act. And so you could think of credit card fraud detection. You could think of it in terms of detecting a virus mutation if you're designing better drugs to combat HIV. Classifying is a customer. Should you approve a transaction for a customer or not? A lot of this is now done with machines. Batteries stretch. That's problematic. Okay, back. Ranking, some problems like personalization, as the sort of things on the web that we used to. Summarizing, that's a big part. You bombard. There's a million reviews for this hotel. You don't read them all. What you want is a summary, and a lot of companies invest a lot of machine learning to provide you with that summary. And ultimately, robotics. I mean, robots are getting better all the time. A lot of the Amazon factories use robots. And the cars, you could call the self-driving cars that will hopefully join us very soon are robots. And making these technologies into machines that can help us is essential to make them a reality. But even in terms of making traditional tools just more efficient, like being able to come up with optimize how you integrate products that are being developed by different teams in large software projects, compiler tuning, trading, and so on. It's particularly useful when you don't have, where there's no human expertise available. So if a robot is navigating in Mars, you can't communicate at a fast rate enough to command a robot in Mars from Earth because of the delay to send a signal and the window at which you can send a signal. So you would want the robot to be autonomous, like the one that we put on the Comet. It has to know how to do things by itself. It has to learn how to avoid the new obstacles that it will encounter. As I argued with the video in the beginning, there are lots of things for which we have no idea how our brains do it. To this day, we still don't know. But we shouldn't try to understand all the mysteries of perception in order to build a vision system. And so learning gives us a fast way to solve that problem. A lot of problems keep changing. So if you're trying to offer products to people, it might be that their preferences will change over time, and so you need to automatically adapt your products. And so learning is about adaptation to the environment to improve on some objective. Of course, sometimes you also need learning solutions because you want to develop a product, but this product should be different for each person. Because, for example, you want to build a digital magazine that everyone can read on their tablet, but everyone will have different tastes. And you want to personalize this magazine to each individual taste. You couldn't just go and program this by hand. So you kind of want that machine to learn. You want there be a learning machine per tablet, per person on the planet. Or even some of these biometric devices, like the digital persona here. And also, some problems are too vast for humans to comprehend. Like here I have things like matching ads to pages and so on, which a lot of the big money in machine learning is in advertising. But also I think there are some problems in the world that humans are incapable of solving, like how to fix our economy. We're doing an atrocious job at it. By how to fix how to manage our environment in an intelligent way. We're terrible at doing that. So there are some problems for which I really hope we can one day build machines that will help us. Will help our econometricians, our senior politicians, and so on make better decisions. What are the challenges? Things we can't do yet. We're not very good at one-shot learning. What I mean by that is this. So the three things that I've shown you there in red are TUFAs. Okay, so how many of you think this guy here is a TUFA? Where I have my cursor. Not many people. How many people think this is a TUFA? About half of the people. How many people think this is a TUFA? More people. Okay. So you've only seen, like I've told you, three things are a TUFA. I doubt that any of you knows what a TUFA is, or has even seen a TUFA before, or heard ever of a TUFA. But you very quickly learn what a TUFA is. That very quick learning. If I'm playing a video game, if I see someone playing a video game and I saw that they did like something smart that gives them lots of points, I'll need to see it once, and I get it. Our machines are not that smart. We don't know how to do that very quick learning. That immediate inductive leap is something we don't have. you want to learn in one task, and what you learn doing in one task, you want to transfer to do another task. That's going to be one of the things that I'm going to be posing as a big challenge of things that we still have to do well. A big challenge is scaling to make these models larger. And the problem is, as we make these models larger, they're consuming a lot of energy. My brain consumes about 40 watts, so less than one of these lights here. So it's extremely cheap to run. But a convolutional network used for vision by any company is taking a lot of energy out of this planet. And there's still a huge gap there in energy efficiency that we need to address. We still don't know how to generate like the world in the sort of in the HD richness that we can generate. And then there's going to be other challenges that are about putting components for perception and action together. So these are things I will not be able to solve in this course, but I want to kind of give you an idea of what it is that people are trying to solve now in going ahead. Okay, so in the next lecture, we will go into the simplest possible model, and then we will build on that. And so by the second week, we will be looking at models with one neuron. By the third week, we will be looking at arbitrary models. By the fourth week, we will be doing the convolutional models used for vision. And at that stage, I hope in your practicals, you'll be implementing these and trying them out. Then there's a few things you have to do. Then I'm going to try to look at this issue of generating realistic signals. Then we're going to look into study sequences, how we can do translation and so on. And finally, we're going to end up at decision making, having these agents that learn to act upon the world using these models. The only limiting factor for you will be the fact that in your experiments that you won't have a big farm of GPUs that you can use to actually train on all the data, or you won't have all the data either. And so access to enough computing resources. From our end, we'll do the best to make sure that at least you get on some reasonable data sets, get to experience this. And Brandon, I know, is working very hard to ensure that you have this. Okay, so I'll see you back here in 10 minutes. Thank you.